In this lesson, we'll discuss sections 9 and 10 of chapter 14. Section 9 is the effect of structure on acid-base properties. Potentially, any molecule that contains a hydrogen atom could be an acid. However, there are some that just aren't. For example, these molecules here have hydrogen, but they are not acidic. The carbon-hydrogen bonds are strong, so it's hard to break off a hydrogen ion or proton. So when we're looking at hydrogen bonded to some atom X, there's basically two things that we want to take a look at to decide if we have an acid. We're going to look at the strength of the bond between the hydrogen and that atom. So strong bonds will hang on to the hydrogen and won't be proton donors. And then we'll look at the polarity of the bond. Less polar bonds will hold on to the hydrogen better and won't tend to dissociate in water. Take a look at this chart where hydrogen is bonded to a halogen. We've got HF at the top and HI at the bottom. The bond between hydrogen and fluorine will be the most polar. Remember, fluorine has the highest electronegativity. And then the bond between the hydrogen and the iodine will be the least polar of the ones that are listed there. We have 3 out of the 4 acids, which are strong acids, HCl, HBr, HI, but HF is weak. HF has the highest bond energy or bond strength as shown in the chart. So that's the strongest bond. So it tends not to donate that hydrogen ion, to be a proton donor. So that's what makes it a weak acid in water. Now let's talk about the importance of structure in oxyacids. So hydrogen bonded to an oxygen bonded to some atom X. These first 4 acids in the chart all have hydrogen and oxygen and chlorine, just different numbers of oxygens in the oxyacids. The more oxygens in the acid, the more the electrons are drawn away from that hydrogen bonded to the oxygen. So that means it's easy to remove that hydrogen ion, that proton, for it to be an acid. So the hydrogen ion or proton in the perchloric acid is easy to remove. And we see a large Ka value listed for this strong acid. Notice for the HClO, that's the smallest Ka value. So it is not very good at donating this hydrogen. Still thinking about hydrogen bonded to oxygen, bonded to some atom X, we can look at electronegativity with similar molecules to see where we have stronger acids. In the chart, the Ka for the HOCl is higher than the HOCH3. So the HOCl is a stronger acid. The reason it's stronger is because its electronegativity is so high. It's good at attracting, drawing electrons toward itself in the bond, and then as a result, that hydrogen ion or proton can be donated. As you know, salts that contain highly charged metal ions form acidic solutions, as shown in the equation. We go from 6 waters to 5 because this complex ion is a proton donor. You can see that the water becomes hydronium. And if we have hydronium in solution, we have an acidic solution. In the diagram, you can see how 6 water molecules attract to a highly charged aluminum ion and form the complex ion. Here we see the aluminum ion bonded with one water molecule, and that high positive charge on the aluminum ion is attracting the electrons away. So then we're able to break this bond and have a proton donor. In section 10, we're talking about the acid-base properties of oxides. So we're still thinking about compounds that have hydrogen bonded to oxygen, bonded to some atom X. And we're going to look at both acidic and basic behavior in water. If we have an acidic oxide or an acidic anhydride, our atom X is going to have a very high electronegativity. And because of that, we're going to have bonds that are covalent and strong. So we're talking about oxygen bonded to this atom X. So if we put this compound in water, that bond remains intact, and then that hydrogen that's bonded to the oxygen is donated, is released. And so that's an acidic solution. Here are some examples. These are non-metal oxides, and that's what gives us the covalent bond between two nonmetals, between oxygen and some other nonmetal. So here's an equation that shows SO3 and water combining together to make sulfuric acid. So here is our HOX combination. And we can then talk about removing this hydrogen ion or proton, and then it's an acidic solution. This bond here between the sulfur and the oxygen remains intact, as described up here. So, nonmetal oxides in water are acidic. For basic oxides or basic anhydrides, X is going to have a low electronegativity, and that oxygen X bond, again, still talking about the hydrogen bonded to the oxygen bonded to X, okay? So the oxygen X bond is going to be ionic this time instead of covalent. And then we can break that bond and make a basic solution. Here are some examples. These are oxides of metals from groups 1A and 2A. So it's a metal, nonmetal combination, but that nonmetal is oxygen. So calcium oxide in water makes calcium hydroxide. Calcium hydroxide is a soluble hydroxide, a strong base that will produce hydroxide ions in solution and therefore be basic. So group 1A and 2A metal oxides are basic oxides. Now please try the problems listed here from the problems at the end of chapter 14 in your textbook.